Introduction. Magnetic fields produced by electric currents are a fundamental concept in electromagnetism, and Ampere's law provides the mathematical framework for understanding this relationship. According to Ampere's law, a current-carrying conductor creates a magnetic field whose magnitude decreases with distance from the wire and is directly proportional to the current. For a straight wire, the magnetic field is given by B equals 0 I/2 pi r, where B is the magnetic field, I is the current through the wire, r is the distance from the wire, and 0 is the permeability constant. When this idea is extended to a coil, each turn of wire contributes its own magnetic field. Inside the coil, these contributions add together, creating a stronger and more uniform magnetic field along the coil's axis. The magnetic field inside a long, tightly wound coil is described by B equals N0 I/L, where N is the number of turns and L is the length of the coil. This equation predicts that the magnetic field inside the coil should increase linearly with the number of turns, assuming the current is kept constant. The purpose of this experiment is to test that prediction by investigating how the magnetic field inside a coil changes when the number of turns is doubled. By designing a procedure that allows us to vary one quantity, in this case, the number of turns, and measure the corresponding magnetic field using the available equipment, we can determine whether our data supports the theoretical model. We collect magnetic field readings for two different coil configurations and compare them to the values expected from the theoretical equation. Graphs and tables are created to show the relationship between the number of turns and the measured field, and a curve fit is applied when appropriate to evaluate how well the experimental trend matches the predicted linear behavior. Overall, the introduction of Ampere's law and the coil field equation provides a clear theoretical expectation. Doubling the number of turns in a coil should roughly double the magnetic field inside it. The goal of our experiment is to test this expectation and analyze whether the measured data confirms the proportional relationship predicted by electromagnetic theory.
DC power supply provided. The adjustable voltage used to set and maintain a constant current for all coils. Set of coils with different numbers of turns. 200-turn coil, 400-turn coil, 800-turn coil, 1600-turn coil. These coils allowed us to compare how the magnetic field changes as the number of turns increases. Magnetic field sensor, Hall probe, used to measure the magnetic field at the center of each coil. Multimeter, used to monitor the current and ensure it stayed the same for all coils. Connection wires, alligator clip leads, used to build the circuit between the power supply, coils, and ammeter. Data collection interface, computer software, used to display and record the magnetic field readings from the sensor. Coil stand or clamp, if provided, held each coil in place, so the magnetic field sensor could be inserted consistently at the center. We started by setting up the basic circuit. We connected the DC power supply in series with the coil, an ammeter, and the necessary connecting wires. We asked for a magnetic field sensor, connected it to the interface, and calibrated it before collecting any data. We placed the magnetic field sensor at the center of the first coil, so that it measured the magnetic field. Along the axis of the coil, we selected a safe target current of 0.1 amps that all coils, 200, 400, 800, 1600 turns, could handle. We slowly increased the power supply voltage until the ammeter displayed that target current. With the current stable, we recorded the number of turns on the first coil, 200 turns. the exact current and the magnetic field reading at the center. We turned off the power supply and replaced the 200-turn coil with the 400-turn coil, keeping the rest of the setup unchanged. We'd placed the magnetic field sensor in the same center position, inside the 400-turn coil, making sure the orientation matched the previous measurement. We turned the power supply back on and adjusted the voltage until the ammeter again reached the exact same target current used for the 200-turn coil. We recorded the number of turns 400, the matched current and the magnetic field reading. We repeated this same sequence for the 800-turn coil. Power off. Swap coils. Place sensor at the center. Power on. Adjust to the same target current. Record turns, current, and magnetic field. We repeated the procedure one last time for the 1600-turn coil and recorded the matching current and magnetic field value. When needed, we repeated measurements to reduce random error and used the averaged magnetic field values for each coil.
Hello, my name is Said Gregorio Canton, and today I will go over the data analysis for lab number 9, Ampere's Law. This experiment is different from the rest, as this time we have to set up the experiment ourselves. The main idea is to compare both theoretical and experimental values of the magnetic field created in a coil of varying number of turns. As you can see, this is the formula that we will be using. This is a magnetic field strength measured in teslas. This is n number of loops or turns in this coil. This value over here, lambda, is permeability constant. This right here is current, and all of that is divided by the length of the coil, which basically is this length right here, for illustrative purposes. Our experiment was set up in which we first have to calculate theoretical values for the 4 coils that we will use, each of them varying in the number of loops. That is the independent variable in this experiment. We would then use software to calculate the actual experimental data of the magnetic field. And then we would use another table to compare the percent error in the number of loops between the theoretical and experimental data that we were given. Theoretical values, here we have to calculate the magnitude of the magnetic field for a coil with 200 turns. Over here, 400 turns, 800 turns, and 1600 turns. We see right here that the constant remains the same in each one, and we also use the same current for our setup, which was 0.1 amps. The length also remained the same, meaning that our only differing value is n, that is the number of loops in the coil. These are the values that were given from our calculations. Set up the data, the magnetic field magnitude, our current, which remained constant for all of these, and the number of loops in each coil. We were able to get this experimental values. We use the same coils, 200 loops, same current, and we arrived at these values over here, experimental. They are in milliteslas, so it is just teslas times 10 to the power negative 3. Finally, we're able to calculate our percent error. For the 200 loop coil, we arrive at a 64% error, 400, 67, 800, 62, and 1600, 60% error. We observe that this percent error is quite high for all of these iterations. All of these coils do in fact have a similar percent error between them, which does speak to some certain level of accuracy, but perhaps our setup did come in short when using the software to read the magnetic field magnitude, or perhaps it was something more of our way of going around the calculations, since we used the same current for all of these. Maybe some variation could have gave us better percent errors. But as it is, these are our results. Thank you for watching.
In this lab, we investigated how the magnetic field inside a coil changes when the number of turns is doubled. According to Ampere's law for solenoids, B equals N times mu naught times I divided by L. The magnetic field is directly proportional to the number of turns. This means that if the current and the length of the coil remain constant, doubling the number of turns should ideally double the magnetic field strength. Our experimental measurements supported this relationship. When we increased the number of turns from 800 to 1600 turns, the magnetic field increased from 1.844 milliteslas to 4.048 milliteslas, which corresponds to approximately a 120% increase. Comparing our theoretical expectations with our measured values showed that the overall trend matched Ampere's law. Though some deviations occurred, these differences likely came from factors such as imperfect alignment of the magnetic field sensor, variations of how tightly the coil was wound, residual magnetic field in the room, and the limits in the sensor precision. Despite these sources of error, the percentage difference between the theoretical and measured magnetic field values was approximately 63%, which is still reflected the same proportional behavior predicted by the formula. Overall, the experimental confirmed the magnetic field inside a coil increases proportionally to the number of turns, consistent with Ampere's law. The data collected in Table 2 and Table 3 clearly showed a direct relationship between turns and magnetic field strength. This supports the conclusion that doubling the number of turns approximately doubles the magnetic field, validating both our theoretical prediction and experimental approach.
Credits: Introduction, Geomaterials and Procedure, Pedro Data Analysis, Seith Conclusion, Aaron.